In particle physics, we were discussing the symmetry and conservation principles. In fact, in this regard, today we are going to discuss a very important conservation principle of charge conjugation. When you say charge conjugation, what does it actually mean? In fact, charge conjugation is a symmetry operation in which particles are transformed into antiparticles and vice versa. It means by the symmetry operation of charge conjugation, we get a particle is transformed into its antiparticle, and if this operation will be performed on an antiparticle, that antiparticle will be transformed into its particle. Okay. In fact, during this charge conjugation operation, not only the sign of charge of the particle changes, sign of charge of particle will be definitely changed, but along with it, the other properties which are all related to charge also gets changed. But all those properties which are not related to charge of the particle, those properties are actually not affected by this symmetry operation. So I have mentioned it here that charge conjugation is a symmetry operation which changes the sign of charge of a particle without affecting any of the properties unrelated to charge. It means those properties which are not related to charge, that will not change after this symmetry operation, but due to this symmetry operation, the sign of the charge will just reversed. If the particle has positive charge, then after this symmetry operation, the charge of the particle will become negative. And if the particle has negative charge, after this symmetry operation, the charge will become positive. Okay. And as I have told you that actually by this symmetry operation, there is just a conversion or transformation of particle into its antiparticle and antiparticle into its particle. So I have mentioned it here that it is a transformation between particle and its antiparticle. Okay. Now, this charge conjugation remains invariant or it remains conserved only in two interactions. The first one is a strong interaction and another is electromagnetic interaction. In fact, until about 4 decades ago, it was believed that the entire universe is invariant under the charge conjugation. But at the end of 1956, experiments revealed that weak interaction violated it. So now it is well known that this charge conjugation remains invariant under the strong and the electromagnetic interaction, but it does not remain conserved in weak interaction. So remember it. Charge conjugation remains invariant under a strong and electromagnetic interaction. Okay. But this symmetry process does not remain conserved in weak interaction. When you say that it is not conserved in weak interaction, what does it mean? It means actually actually the weak interaction does not distinguish between a system and its charge conjugate. It means in weak interaction you cannot differentiate before the operation what is the particle and after operation what will be the particle. You cannot distinguish it. So we simply say that in weak interaction that this charge conservation, this charge conjugation does not remain conserved. Okay. As I have told you earlier that when this charge conjugation operation is performed, then there is not only a change of electric charge or magnetic moment, but the sign of other quantum numbers which are related to actually charge also gets changed. For example, you can see that the hypercharge Y, the Baryon number B, and lepton number Le and L mu. Le is the lepton number corresponding to electron, and L mu is the lepton number corresponding to muon. All these quantum numbers also get changed in its sign after the charge conjugation operation. But there is no change in mass of the particle and spin of the particle. Okay, have you understand that after the charge conjugation operation there will be a change of charge, magnetic moment, even helicity. This will be changed. But not only these things, but also the hypercharge also changes its sign, baryon number also changes its sign, lepton number also changes its sign. But at the same time, after this symmetry operation, there is no change in mass and spin of the particle. Okay. In fact, when you study this thing in quantum mechanics, you see that actually the charge conjugation operator, which is denoted by this symbol C hat, actually it is a unitary operator, and this unitary operator satisfies the following relations you can see here. Actually, C hat Q C hat inverse. Here Q is actually charge, you can see, and this will be equal to minus Q. Similarly, when this operation will be performed on the hypercharge Y, then we simply write C hat Y C hat inverse. This is equal to minus Y. And when this operation is performed on baryon number, then we see that C hat B C inverse. This is minus B. And similarly, in case of lepton numbers, C hat Le C hat inverse, this is minus Le, and C hat L mu C hat inverse, this is minus L mu. Okay. So you can see that this symmetry operation also changes the sign of these quantum numbers, that is the baryon number, lepton number, and the hypercharge too. Okay. Now, when a particle is changed into its antiparticle, but the antiparticle is same as that of the particle, then actually such a particle is called self-conjugate. Have you understand or not? When you say that the particles are self-conjugate or true neutral particles. In fact, there are some particles or elementary particles which are transformed into themselves. That is, there is no change in charge of the particle or any property of the particle after this charge conjugation operation. So if an elementary particle is transformed into itself by charge conjugation, then you can say that such particle is its own antiparticle, and those particles are actually then called self-conjugate or true neutral particles. Okay. When you say that a particle is true neutral particle, that does not mean that the particle is electrically neutral. A particle may be electrically neutral, that its charge is 0, but that may be not a true neutral particle. So true neutral particle and a chargeless particle both are different things. You will see later on, just in this lecture, at the last of lecture, that our neutrino is a neutral particle. It has no charge. But this neutrino is not a true neutral particle. After the charge conjugation operation, we will see that actually the helicity or the polarization state of the neutrino and its antiparticle, that is antineutrino, will be just opposite. Neutrino is actually left-handed polarized, while the antineutrino is right-handed polarized. So we say that a neutrino is not a particle, a neutral particle in true sense. Okay. So I have mentioned it here that electrical neutrality, when you say electrical neutrality, it means the charge of the particle is zero, alone does not ensure that the particle is its own antiparticle. Okay. So if a particle is its own antiparticle, then it is called truly neutral particle. Okay. For example, we will see that a gamma photon is a true neutral particle because its antiparticle is also a gamma photon. Similarly, the neutral pion pi0 is also a true neutral particle. We will see just now that this pi0 is its antiparticle too. It means the antiparticle of pi0 meson is simply pi0. Okay. Like that, eta 0 meson, this is also a true neutral particle because its antiparticle is eta 0. Okay. So I have mentioned it here that gamma, pi0, eta 0, these are actually the true neutral particles. Okay. Now, in terms of the wave function of a truly neutral particle, you can say that if psi is the wave function of a particle, that is a true neutral particle, then if you will perform the charge conjugation operator on this eigenfunction or eigenstate of the true neutral particle, then the new eigenstate will be also the eigenstate of the charge conjugation operator. So I have mentioned it here that the wave function of a truly neutral particle must be an eigenstate of the charge conjugation operator C hat. You can see that if we consider that psi is the wave function of a true neutral particle, then when you will operate this operator, that is the charge conjugation operator C hat, on this eigenstate ket psi, which is actually the eigenstate or wave function or eigenvector of a true neutral particle, then we simply get a new eigenstate which I have denoted by psi c. But this psi c is equal to what? This will be equal to c times ket psi. Here c is actually the eigenvalue of this operator C hat. And actually this C, which is actually the eigenvalue of operator C hat, has an eigenvalue equal to plus minus 1. Actually, how this value is plus minus 1, you can see that in this last part of this equation, it is found that when a two-fold application of this operator C hat will be equivalent to an identity operation, and so that C square will be equal to 1. And C square is 1, so C will be equal to plus minus 1. So in fact, when this charge conjugation operator is operated on the eigenstate or the eigenfunction or the wave function of a true neutral particle, then we get an eigenstate which will be plus minus ket psi. Okay. When you write plus ket psi, it means the eigenvalue is equal to +1, and when you write minus kth psi, it means the eigenvalue of this unitary operator, charge conjugation operator C hat is equal to -1. Actually, this eigenvalue C is also known as charge parity of the particle. Charge parity of the particle. And when this C will be +1, then you can say that the charge parity is positive, and when it is -1, then the charge parity is negative. Okay, so I have mentioned it here that for neutral particles with C equal to +1 have positive charge parity, and C equal to -1 has negative charge parity. Now we will illustrate this fact by some of the important examples. Here you can see, if you consider that there is a single photon and the eigenfunction of photon that is kth psi, I have denoted it here by simply the kth gamma. Okay, so kth gamma will be written now instead of kth psi, and when we will operate the charge conjugation operator C hat, which is a unitary operator, on this kth gamma, which is actually the eigenstate of a single photon, then we get that it is equal to minus kth gamma. So you can say that in this case the eigenvalue or the this single photon has actually a negative charge parity, and C is equal to here -1. Okay, but if there is a system of photons, you consider that there is a system of n photons, then when we will operate this charge conjugation operator C hat on kth n gamma, then we get -1 to the power n times kth n gamma. So you can see in this case of a system of n photons, the eigenvalue is of this operator C hat is -1 to the power n. And in this case you can see that the charge parity in this case may be positive or it may be negative, both. So if n is, let us say, an even number, n is even, then you know if n is even, then -1 to the power n, this will be equal to +1. So in this condition, for this system of n photons, the charge parity will be positive. But if n is, let us say, odd number, then you know that -1 to the power n, this will be -1. So for this system of n photons, the charge parity will be negative. Okay, so from this example you can see that for a single photon or the charge parity is negative. This is definite. Okay, single photon means one photon. 1 is just an odd number, so you can check for an when the number of photon will be odd, the charge parity will be -1. But if there is, for example, let us say a system of 2 photons, then in that condition the charge parity will be positive, because 2 is an even number and -1 to the power 2 will be +1. So I have mentioned here that for n photon state, for the n photon state is also an eigenstate of this operator C hat with eigenvalue -1 to the power n. Okay, I hope you have understand this fact very well. Now we take another important example of the true neutral particle, and this example is actually of pi zero meson, that is neutral meson. Actually, you know that this neutral meson is decayed into 2 gamma photon. Pi 0 decays into 2 gamma photon. And you have just seen that the gamma photons are actually self-conjugate particles. So definitely, since the decay of pi 0 takes place into 2 gamma photons and gamma photons are self-conjugate or true neutral particle, so definitely this pi 0 meson will be also a true neutral particle. Okay, and in this case, when we will operate the unitary operator, that is the charge conjugation operator C hat, on the eigenstate k pi 0 of this neutral pi meson, then we get it is equal to k pi 0. It means in this condition you can say that this pi 0 meson has a positive charge parity, and this pi 0 meson is a self conjugate particle. Okay, but on the other hand, you can see that this pi plus meson and pi minus meson are not actually the self-conjugate particle, and because in this case you can see when the charge conjugation operator C hat is operated on the eigenstate k pi plus of this pi plus meson, then we get minus pi k minus. Actually here k minus represents an eigenstate. So you can see that the eigenstate has been changed. Here the eigenstate in LHS you can see the eigenstate is k pi plus, and in RHS it is k pi minus. Okay, and similarly when this operator C hat is operated on the eigenstate of pi minus meson, then we get the eigenstate of pi plus meson, that is minus pi plus. So we can say that these two particles are not the eigenstates of C. So I have mentioned it here that k pi plus and k pi minus are not the eigenstate of C hat. Okay. Now, as I have told you earlier that although you write that neutrino has no charge and the anti-neutrino has also no charge, but these two particles are not true neutral particles. True neutral particle. It means when this operator C hat is operated on the eigenstate of neutrino nu, then we actually get the eigenstate of the nu bar. Okay, and it is found that the polarization state of the neutrino is and the anti-neutrino are not same. In fact, it is seen in the experiment that the polarization state of a free neutrino is left-handed, while that of the anti-neutrino is right-handed. Okay, so neutrinos are the examples of particles which are not truly neutral, although they are electrically neutral. Electrically they have no charge, but in real sense you can say that these particles are not true neutral particle on the basis of charge conjugation operation. Okay, so charge conjugation applied to a free moving neutrino then results in a process which does not exist in nature. Okay, so when we will operate this operator on this, then we find its antiparticle, and such process actually does not exist in nature. So these were actually some important facts regarding the charge conjugation. This question is actually asked in the short answer type question, and also for objective problems this is very important. So remember all the facts which I have discussed here, and then you will be able to write the correct answer of the objective problems asked in your different examinations, and also the questions of short note type you will be able to write the correct answer. So these were some of the important facts regarding the charge conjugation. Now in the forthcoming lecture, we will see the another invariance principle, that will be actually regarding the parity. So let us wait for the next lecture, and I hope you will enjoy the next lecture too, as you have loved my previous lectures. So you will give your love for the forthcoming lecture. It is my belief.